Allora, oggi in questo colloquio farò una overview molto generale e come target ho preso gli studenti undergraduate sul diagramma di fase della QCD, Quantum Chromodynamics. Allora, il piano del talk è il seguente. Farò un'introduzione alla QCD e in particolare a due proprietà della QCD del vuoto, che sono il confinamento da una parte e la rottura della simmetria chirale dall'altra. Dopodiché comincerò a presentare cose leggermente più esotiche, ovvero legate al deconfinamento e alla ristorazione della simmetria chirale, sia a temperatura finita che a densità finita molto grande. E infine il clou, diciamo, il climax, sarà sulla presentazione, la discussione di come tutti questi ingredienti aiutano a disegnare il diagramma di fase della QCD. Prima delle conclusioni farò un breve commento su come questo diagramma negli ultimi anni è stato improved, aggiungendo nuove direzioni lungo le quali muoversi. Allora, per cominciare, facciamo una introduzione. Ah, ma forse c'è qualcuno online che lo vuole in inglese. Mo' ci sto pensando. No, se non c'è nessuno online. Please, per favore, togli quello. Yeah, so eventually we do that in English. Okay, very good. So when we talk about quantum chromodynamics, namely QCD, we have in mind the bigger picture for the fundamental interactions. Okay. Now it is well known that so far we have evidence that there are at least 5 fundamental interactions. I should say 3, but we can say 5. These are the strong interaction, which will be the main topic of this talk. Then we have the gravitational interaction and electromagnetic interaction on the one hand. On the other hand, we have the weak interaction, as well as the interaction with X particles. Però non funziona più questo. Ma è assurda, stai? Come? Okay. Now it should work. It should, hopefully. So, I think it should be familiar to everyone in this audience. What is electromagnetic interaction and what we mean by electric charge? For example, we know, I think since middle school, that if we take two point charges, let's say Q1 and Q2, they will experience a force, which is the Coulomb force. And this allows us to define operatively the electric charge of the system. In particular, we can define electric charge also for elementary particles. And we know that in order to describe all the electromagnetic interactions, we can introduce just one operator, which is called electric charge. And this can take different values depending on the particles. So, for example, the proton, as well as the positron, the pi plus, will have charge in some units equals to +1. The electron can take charge -1. The quarks can take charge +2/3 or -1/3, depending on the type of quark that we consider. Anyway, we have only one quantity that we call the electric charge. Now, if we want to describe the electromagnetic interaction at fundamental level, we have to use quantum field theory. And in particular, the theory that describes the electromagnetic interaction from the point of view of quantum field theory is called quantum electrodynamics, or QED. So basically, here there is the Lagrangian density for QED, in which you have one term that describes the dynamical photon field. Then we have another term that I wrote only for one species of fermions, which describes the interaction of the fermion that can be an electron as well as a quark. It doesn't matter. with the electromagnetic field. Now, one thing that I think you should know, but just in case I refresh this idea in your mind, is that QED is based on the principle of gauge invariance. Now, gauge invariance means that if we change the electromagnetic field according to this relation here, where theta is a function of space-time, and simultaneously we change the fermion fields like this, then any physical observable is unaffected by this change, which means, in other words, that we cannot measure the phase of the fermion fields. Okay? Now, from the point of view of group theory, if we consider these transformations on the fermion fields, these belong to one special group, which is called U1. So we call this set of transformations the U1 gauge transformations. And we say that QED is invariant under U1. Now, the topic of the talk is the strong interaction. So in order to do that, we first must understand when and where the strong interaction is important. So basically, the strong interaction is important at very microscopic level. In fact, at the level of atomic nuclei. Now, what we know after many experiments and also theory building is that if we consider scales that are smaller and smaller inside the atomic nuclei, then there are elementary constituents inside the nucleons, the proton of the neutron, which we call the quarks. Okay. Now the quarks become very important in our world only for length scales that are much smaller than the scale of the atomic nuclei. So they become important if we consider lengths that are of the order of 1 fermi, or even smaller than 1 fermi. Now, in the modern view of the strong interactions theory, what we know is that quarks, which are the main ingredients of this new interaction, have 3 charges. Now we call these 3 charges as the color charges. And by matter of convention, we label them as red, green, and blue. Remember, for QED, we had only 1 charge, which is the electric charge. Now, similarly to what we have done in QED, in QCD, we can make up a new interaction Lagrangian using the gauge principle. Namely, we make the assumption that the strong interaction theory is invariant if we locally, means space, point by point in space-time, we make a reshuffling of the color charges. So this reshuffling means the following. Take, for example, one quark, which is completely red, which means that it has red equal to 1, green and blue charge at 0. Then we make a transformation to reshuffle the color. For example, one particular transformation is one that changed the red quark into a blue quark. So you have a new quark in which blue is 1, red and green is 0. We make the assumption that this transformation does not affect any observable. So any quantity we can measure, so that is physically relevant, is not affected by this change. Since we have 3 colors, this transformation is 3-dimensional, we call that SU3. Okay. Now, of course, in general, if we take one red quark, for example, it is not necessary that we go to a new quark which is blue or green. In general, this is a combination of all these quarks. This can be achieved formally if we introduce this transformation that, as you can see, depends on these generators that we denote by TA. Now, this group generated by this TA has the property that if you take the commutator of 2 generators, say TA commutator with TB, this is non-zero. In fact, it gives a combination of other generators. This quantity here, F, ABC, is what we call the structure constants. And as I usually said to the students, these FABC are the cornerstone of the strong interaction. In fact, everything which is nonlinear related to strong interactions is embedded in these constants here. And I will show that explicitly in a moment. So QCD, which is the modern theory of strong interactions, is a gauge theory which is based on the SU3 gauge invariance. The quarks are certainly very important ingredients in this theory. As I said, they have 3 colors, because there are 3 charges for these quarks. To be more complete, we also should talk about the flavor of the quarks. Usually flavor can be up, down, strange, charm, beauty, or bottom and top. So we have 6 flavors of quarks. I will consider only 3 flavors, up, down, and strange, because these are the lightest. So are the most important for all what I'm going to say in this talk. Now, besides the quarks, we have the gluons, similarly to QED, in which we have charge on the one hand, and we have the photon field on the other hand. Now here, the strong interaction is mediated by the gluons. As I said, since we are using a gauge group which is non-abelian, that FABC that I was mentioning before directly affects the properties in which gluons interact among themselves. In fact, for example, the gluons can interact via this 3-body vertex, which is proportional to FABC. And we also have a 4-body interaction, which is proportional to FABC, FABE. These self-interactions of the gluons are very important to understand the properties of the strong interactions, in particular at very large energy, also at small energy, in all the range of energy, actually. This is why I say that these FABC are really the cornerstone on which QCD is based. Now, one of the things that makes QCD, so the strong interactions, different from the theory of electrodynamics, is that actually the strong interactions become weak when energy is very large. In fact, here I'm showing in this qualitative plot the behavior of the couplings in QCD on the one hand, which is the solid line here, and the behavior of the QED coupling, the dashed line here, as a function of the energy scale. Now we see that while in QED, increasing the energy results in an increase of the coupling, in QCD, the opposite takes place. Increasing the energy, the couplings become smaller. This means that in the very large energy regime, quarks basically are almost free particles. This thing is called asymptotic freedom. Asymptotic because it happens at very large energy. Freedom because quarks are almost free. When we talk about this thing, we realize that in QCD, there is a peculiar scale that we denote by lambda QCD, which is the energy scale that comes up dynamically in the strong interaction theory, which tells us basically at which energy scale or at which momentum scale strong interactions become strong. In particular, if energy or if momentum exchange is much larger than this lambda QCD, then we have asymptotic freedom, so quarks are almost free. On the other hand, as energy exchange or momentum exchange becomes of the order of lambda QCD, quarks become very strongly coupled. Now, one thing that you might notice already is that when we define the QCD, we talk about quarks and gluons, right? However, if you look around ourselves, we do not see quarks and gluons. At least we do not see free quarks and gluons. We see hadrons. We see protons, neutrons, ions, and so on. The reason is that, not as one Chinese professor said that QCD is wrong, but the reason is that quarks and gluons are confined within atoms. Technically, it means that quarks and gluons are not asymptotic states of QCD. Practically, it means that we cannot see them because they live inside the nucleons and the pion for the chaos inside the atoms. So they are confined. Let's see what we mean by confinement. So to begin with, let us consider QCD in the limit of static quarks, which means that we have QCD with gluons. We put quarks, but we assume that the mass of these quarks is very, very large. So basically, these are static. They just sit in this gluon bath. And we imagine to measure the potential between one of these quarks and one antiquark. The result of this would give the potential, which is shown here. Now, when the distance between the quark and the antiquark is small, we would find nothing but the standard Coulomb-like potential. So an attraction follows the Coulomb law vector between this quark and this antiquark. However, when distance is very large, you see, the potential increases linearly. This means that if we take this quark and this antiquark, which are very heavy, and want to split them apart, increasing the distance, we must increase the energy that we must put in the system to split them. So in principle, if we want to split them at infinite distance, we must give infinite energy to the system, which of course is impossible. This is a signal that the quarks are confined. Namely, it is not possible to split one quark from its antiquark companion. Okay. Now, QCD not only has the local gauge symmetry, but also has global symmetries. Now, of course, I will not go into details here in this colloquium. I just mentioned that this symmetry means that, actually implied that the strong interaction conserved the baryon number as well as the isospin. In fact, what we learn in the course is that the good approximation interactions in the nuclei are isospin symmetrical. Okay. Now, in principle, if one takes just the Lagrangian density of QCD, one would expect an additional isospin conservation, which I call the chiral isospin conservation. Now, to understand the chiral in a very simple manner, let's think about our hands. In fact, chiral comes from the English chiral, which means literally hand. Okay. Now, if you take your hands, the left hand and the right hand, you know that they are the mirror image one of the other. But if you try to overlap them, they do not overlap. This means that our hands are chiral. Okay. Now, for particles, we can also define chirality in some little bit tricky way. But for this talk, let us consider only massless particles. So in this case, a left particle, say a left quark or left electron, simply means that the momentum of this electron is anti-parallel to its spin. Instead, the right quark, or the right particle in general, means that the momentum of this quark is parallel to its spin. Okay, for massless particles, this is enough. Now, we can make a chiral transformation, thinking to our hands, and we rotate, for example, the left hand with an angle minus pi half. So we get this. And the right hand, we rotate that with an angle which is plus pi half. So you see, we rotate the left component, the left hand, and the right component, the right hand, in a different fashion. Now, this transformation on the level of particle physics would leave the Lagrangian QCD invariant, unless one considers small mass terms. However, what happens is that the QCD vacuum does not respect, this symmetry. In fact, what we can see is that in the QCD vacuum, there is an operator which is psi bar psi, whose condensate is non-zero. The non-vanishing of this operator in the QCD vacuum means that this chiral symmetry is broken spontaneously by the QCD vacuum. And if we look for some qualitative interpretation of that, we can say that this breaking of chiral symmetry in the vacuum means that the vacuum is filled with many quark-antiquark pairs that fluctuate and create long-range correlations, like the ones that we had in the quantum fluid, for example. Which means that, for example, if we consider one quark or one antiquark, it doesn't matter, which propagates in the QCD vacuum, it takes contribution from this condensate. So, roughly speaking, the mass of this quark becomes very heavy due to this interaction. Okay, so this leads to some measurable effects. In fact, the effect of this chiral condensate, for example, appears in the spectrum of pions and gluons. So, the QCD vacuum that I discussed so far is something that is characterized by confinement as well as chiral symmetry breaking. Okay. Now the question is, what happens if we take the QCD vacuum and we put that at very large temperature or very large density? So to begin with, I will consider the case in which we heat this QCD vacuum and see what we expect. Now, one of the reasons why we would like to understand what happens when we heat up the QCD vacuum is given by the study of the very early universe. In fact, it is accepted that in a very early stage of the universe, so after the Big Bang, there was a finite time range in which the temperature was very, very large. That if you want to understand, for example, the equation of state of this medium and to study the evolution of this medium during the expansion of the early universe, we must know the behavior of the strong interactions in this regime. So to do that, we have to study not vacuum QCD, but very hot QCD. Now, what we would expect when QCD becomes very hot is very simple to say. Consider a box which is filled with QCD vacuum, so it's empty. Then heat up this box. What we know, what we expect, is that as the temperature becomes quite large, there will be the excitations of, for example, pions and antipions, or chaos, counts, and I don't want to say counts of pions, K plus, K minus, okay, and other particles. And of course, as we increase this temperature, the number of these mesons which are excited will be very, very large. Which means that even though the baryon number, the net baryon number will remain 0, we will have in this box a lot of these meson fluctuations, meson excitations, which means that they will start to overlap with each other. So eventually, the density of these particles will be so large that it will be no longer meaningful to talk about one quark which is confined inside, let's say, one pion. But due to this overlap, it will be possible that one quark which lives in one pion will propagate to the other pion. So basically, you are making a new medium in which quarks are no longer confined within one single atom, but they start to communicate with the quarks and the gluons which are in the other atoms. So we expect, at least very likely, that increasing the temperature, we will have something in which color will be deconfined. This absolutely yes.
Okay, but in order to have that, you should have the high density of.
No, high temperature is enough.
Just high temperature.
Yes. Because you populate pion states. So baryon density is 0.
Okay.
You have pions and antipions. So they do not carry baryon number. So baryon number is 0. So baryon density is 0. But the particle density is finite. Just think of the Boltzmann distribution, for example, or the Boltzmann distribution. Since the pions are massive at 0 temperature, they are suppressed. If you increase the temperature, there is exponential minus m over t. Right? So the population becomes more and more important. So it's just thermal fluctuations. I mean, thermal population. Is okay?
Yeah, I was just thinking if you have like, yeah, because you said that the quarks like becomes like, is there is a sort of like plasma, right? So
yes, exactly.
Change like quarks. Yes.
Yes.
So that's why I was thinking that.
Yeah, but that does not meet baryon density. If you have a gas made of many pions which overlap with each other, so the baryon density is 0 because they don't carry any baryon number. So, which means that you have equal number of quarks and antiquarks. In fact, you have pions and antipions on the same footing, right?
Okay.
But they can still migrate. Okay. Now, of course, this is a very naive qualitative picture, but this picture is confirmed by actual calculation done in QCD. In fact, here on the left panel, I plot the pressure, energy density, as well as entropy density, but it is not important in this context, of this QCD vacuum as a function of temperature. And as we can see, there is a time and temperature range around 150 MeV, in which there is a rapid increase of the pressure as well as of the energy density as the temperature increases. Moreover, if we compute the chiral condensate, that condensate I was discussing before in the QCD vacuum, we compute that at finite temperature. What we find is that, again, in that temperature range, there is some lowering of this condensate. Now, if you remember, when I talked about the chiral condensate, I said that is the signal that chiral symmetry is broken in the QCD vacuum. Now we find that at large temperature, the chiral condensate drops to a very small value, which means that chiral symmetry gets restored at large temperature. So at very large temperature, we have a medium in which chiral symmetry is restored, at least approximately restored. And let's have a look at confinement. Here is the potential of the quarks, actually quark anti-quark potential, at different values of the temperature. Now, when temperature is small, in agreement with the confinement picture, what we find is that the potential increases linearly at large time. Now, increasing the temperature, we see that this linear regime drops down. In fact, when temperature is very large, the potential at very large separation becomes flat, like the Coulomb potential. If we take a look at the confining term in the potential, the linearizing potential that I was discussing before, and we look at this data implies that when temperature is very large, this constant, which is called the string tension, drops to 0, which means that at very large temperature, the QCD medium loses the confining property. Okay, so in the high temperature phase of QCD, we have deconfinement and we have approximate chiral symmetry restoration. This is a new phase of QCD in which quarks and gluons can propagate freely, almost freely in the medium, is called the quark-gluon plasma. When this name, QGP or quark-gluon plasma, reminds us the fact that now, at very large temperature, the divisor field are quarks and gluons. They are no longer dependents. Okay. Now, this quark-gluon plasma can be produced actually in real experiments that we can make here on Earth. And they have been done at the machine called RIC in the United States, and have been done and will be done also in the machine at CERN in Geneva, the CERN. One of the purposes of these experiments, as we usually say in the community, is that this experiment helps us to create a little bell. Because what we do in this experiment, is that we create a medium, which of course is short-lived in time. But this medium is so hot, in fact, estimates of the initial temperature as around 300 up to 600 MeV, which are quite larger than the critical temperature of QCD, as you can see. So in this medium that comes from these collisions, we form the quark-gluon plasma. Okay. Now, I will not talk about these experiments because due to lack of time. And of course, in this department, there are people that can talk about that much better than me. So what is important is that in these experiments, not only we have the chance to probe actually and to study experimentally the hot medium of QCD, but also we can probe this medium and how it responds, for example, to the presence of very large magnetic fields or very large vorticity, And a few other things that we learn from these experiments is that this medium, which is produced by these collisions, is characterized by having at least close to phase transition by a very small value of eta over S, where eta is the shear viscosity and S is the entropy density of the medium, as well as there is a nice production of collective flows, which means that the medium that we produce is collective medium. So it's not perturbative. What time is it? 22:04. Am I going too fast?
Yeah, be around 45 minutes.
Okay, of course, if you have questions, please ask me during the presentation. Okay, now let's see what happens on the other side. When you have a cold medium, cold QCD medium, that becomes very, very dense. Now, also here, firstly, let me give you a motivation why we want to do that. One of the main motivation, actually, is that the universe is populated with very large, with very dense objects. For example, neutron stars. And according to modern theories about neutron stars, it is possible that at least in the deep core of the stars, the density becomes many times larger than the nuclear saturation density. Which means that at least in the core of the neutron stars, we could have a very, very dense medium. But not only that, because it was also suggested that there are the so-called strange stars, which are stars in which there is no nuclear matter at all. So basically, these are stars made of quarks, which are very, very dense. So it is important to understand how the strong interaction behaves in this very dense regime. So that's why we want to study what happens to QCD when we have a very dense medium. Now, similarly to what we have done for heating the QCD vacuum, we can take some hadrons, for example, the ones that made our own atomic nuclei, and we compress them stronger and stronger. Similarly to what happened when we heated the QCD vacuum, what could happen is the following, that at some point, these hadrons are so much packed, the one on the top of each other, that quarks can actually propagate freely from one of the hadrons to the other hadrons. So in some sense, also in this very dense medium, we are producing a new type of phase of matter in which quarks are no longer confined in one hadron, but they can move among many hadrons. So again, we expect to have a deconfinement phase transition at large density. This argument actually is quite old. In 1970, was suggested in the 1975. So if we compress nuclear matter, what we expect is that we produce another type of deconfined matter. Now we call that quark matter. We cannot call that simply quark-gluon plasma, because now this phenomenon is not happening in the vacuum, but in matter. So we make a transition from nuclear matter to quark matter. Now, the physics here becomes very interesting. Assume that we have only 3 quarks, so no interaction at all, and the system is very dense. It means that these quarks will occupy very large momentum spheres, the Fermi spheres. For example, if we consider the blue quarks, the quarks which are blue will occupy their Fermi sphere. And let me call the radius of this Fermi sphere mu, which is the chemical potential of these quarks. Now, if the quarks are massless, the density of these quarks is proportional to mu to the 3rd power, which you can keep in your mind for what follows. Remembering that when we increase the chemical potential of the quarks, means that you are increasing the density of the quarks. Okay, so these Fermi spheres of quarks, red, green, and blue, is what we call the naive QCD vacuum, or naive QCD matter, normal QCD. Okay, However, what happens is the following. We know that in QCD, there is an interaction which is mediated by gluons. Okay? And there is some particular channel in this gluon exchange interaction, which technically we call that the 3-bar. If you don't understand what 3-bar means, there is no problem. This channel is attractive, which means that even though the quarks occupy very large Fermi spheres, there is an attractive interaction among them. And as we know from the standard theory of superconductivity, take the PCS theory, for example, this means that the Fermi sphere is unstable to the formation of Cooper pairs. Now, in the case of the PCS superconductivity, we have Cooper pairs made of electrons, right? Here we have quarks, so the Cooper pairs will be quark-quark pairs. And similarly to what happens in the PCS theory, we call this new phenomenon the color superconductivity. Superconductivity because we form pairs as in the PCS theory. Color because quarks carry color. Okay? Now, it is possible to make many answers about the particular nature of this color superconducting state. The most popular one is called the color flavor locked phase, or CFL in short. Basically, what's happening here, very roughly speaking, is that because of this quark-quark pairing in the ground state, there is a reshuffling of the colors around the Fermi sphere. And in particular, colors and flavors get mixed with each other. So in normal QCD, we would have, let's say, an up red quark, a down green quark, and a strange blue quark, each of them occupying its own Fermi surface, a Fermi sphere. In this new state in which colors is reshuffled, we will have 3 excitations, which we call quasi-quarks. Similarly to what happens in condensed matter, where we have quasi-particles instead of particles. And these 3 quasi-particles will be a linear combination of these quarks. So you can see in this new state, color and flavor get literally reshuffled among them, okay, as a result of this condensation. Here I want to show you the typical spectrum that we expect for these quarks at very large density. Now, when we talk about spectrum, basically what we mean is that we are showing the energy as a function of the momentum of the particle. Okay? Now, in normal QCD, we would have the dashed line with the node in the spectral relation when P, the momentum, is equal to the Fermi momentum, the chemical potential. So, since there is a point in the phase space in which energy is 0, we say that the system is gapless. Okay? Now, let us consider the quarks in this dense medium. The spectrum will be represented by these solid lines here. In particular, we have 8 quarks, which follow the green line, and 1 quark, 1 quasi-quark, which follows the blue line here. So there will be 1 excitation with this mass here, this gap, and 8 excitations with this gap here. Okay. Now, if you remember the PCS theory of superconductivity, you know that when you have this gap in the spectrum, it means that electrons basically decouple from the theory, at least for the low energy spectrum. For example, this is measurable when you measure the specific heat as a function of temperature. You will get an exponential suppression of specific heat due to this gap in the spectrum. For quarks, so we have a similar thing here. Now, this can be important, as I was mentioning before. Let's think, for example, to a neutron star. You can repeat arguments also for quark stars, okay? Now, for neutron stars, we can actually compute the so-called mass-radius relation. Basically, this is a plot in which we solve the stability equation for the neutron stars. And we find at the given values what is the mass of that star. And now we can compare this prediction with experimental observation. Now, here the blue line, the black solid line, corresponds to a prediction for the mass radius of this star when we do not have quark matter, so pure nuclear matter. Okay? Here, A and B, which means this green line and this pink line, correspond to the mass radius of the star, computed mass radius of the star, in which we have corresponding superconductivity in the core of the star. Now, one of the things that usually one should check is if models are able to reproduce with that equational state the famous almost two times solar mass. I mean the mass of neutron star whose mass is about 2 solar masses. I hope this is clear. Okay, which is represented by this gray band here. And as you can see, it was shown quite recently that actually also neutron stars with a superconducting core can reproduce the quark mass, the masses of the neutron star, whose mass is about 2 solar masses, which is a nice indication that actually course of conductivity, at least from this type of data, cannot be ruled out, and actually could be present in the core of the stars. Now let's turn to the main topic of the talk, which is the QCD phase diagram. Now, if you are wondering what is this mess which is shown here, actually I had fun during these days chatting with ChatGPT, asking what was her or its, depending on how you it's ChatGPT, what is her idea of the QCD phase diagram? And she came up with a lot of stuff, which of course cannot be scientifically correct, but at least it is quite artistic. So I selected a couple. One is now, I put that as a background here to introduce this part of the talk. Another one will appear in a moment. You will understand why I choose that. So, so firstly, what we mean, yeah, this arrives later. Now, what we mean by, first of all, by phase diagram, and then by QCD phase diagram. So the phase diagram of QCD is a diagram usually in the temperature and chemical potential plane, in which we map the expected phase of QCD for the particular pair of temperature and chemical potential. Okay, this is not a typical QCD phase diagram, but it is how ChatGPT gives the phase diagram. As you can see, now Di Marco is everywhere. Barella became Barello. Baroyon chemical potential. Okay, just artistic and fun. Lautaro also is almost everywhere. This should be a Acerbo. Okay, anyway, this may be Chalanov, but I don't know. I would not buy that. Anyway, this is how ChatGPT sees the QCD phase diagram. I was upset because there was only one star here. Now there are two. Right, Mugabe. Yeah, these inside jokes. So actually, the phase diagrams are not only related to QCD, but to any substance that you have in mind will have its own phase diagram. For example, here I'm showing the phase diagram of water, very schematic view of the phase diagram of water that I just borrowed from Wikipedia, in which we have pressure and temperature. So as I was telling, if you choose a value of pressure and temperature, and you go into the phase diagram, you can see if the water will be in the solid state, in the liquid state, in the gas state, and so on. And also can depict the transition lines from liquid to gas, for example, solid to liquid, and so on. Okay? So our goal is to see what this phase diagram becomes in the case of QCD. Now, I did not tell that explicitly when I show the results, some of the results. I will make that explicit now. If we want to study QCD from very first principles, we can do that using a tool, which is called lattice QCD, which basically means that we take the full QCD, we put that on the computer and make numerical experiments and see what comes out. Now, there is no doubt that at least for QCD at zero chemical potential, this is the best tool we have to understand the equation of state. However, this is limited by the fact that it is not possible to make reliable calculations using lattice QCD at finite chemical potential. So unless one is happy to go to the very perturbative regime, which means chemical potential much, much larger than the one present in nature, so in that case, one could use perturbative QCD calculations. The QCD phase diagram in the temperature and biochemical potential plane, beside a very narrow band around equal to 0, should be just a big question mark. If you go to a conference and you show this QCD phase diagram, no one can say anything because this is scientifically correct. However, if we were stopped, by the lack of lattice QCD calculations, then we should stop doing what we like doing, meaning calculations, and we would spend our days doing jokes. I'm showing this not to show Morgana, but to show respect for the flag.
Yeah. Yes. Bruce Lee.
It was obvious. Very good, very good. However, since we are an intelligent species, we can overcome the lack of lattice QCD calculation at finite chemical potential. And we can use our intelligence to make at least some guesses about the shape of this phase diagram at finite chemical potential. So we can do that using models that at least match lattice QCD prediction at mu equal to 0. And then predict with this model when chemical potential becomes very large. Here, there is a recent result about one of these calculations, which shows the phase diagram at finite temperature and finite biochemical potential. So in the vacuum, which corresponds to mu equal to 0, as I said, we have a phase which is the QCD vacuum, which is characterized by having spontaneous symmetry breaking, chiral symmetry is broken, and we have confinement. Now, if we increase temperature, we make a crossover, a smooth crossover to the new phase, which is the quark-gluon plasma, in which chiral symmetry is approximately restored and color is deconfined, in agreement with the picture given by lattice QCD. Okay? So now we can increase the chemical potential and measure within this model how the critical temperature changes by changing the chemical potential. So what we find is that the critical temperature goes down, becomes smaller and smaller. Now, if mu is small enough, this transition from the confinement phase to the deconfinement phase remains a smooth transition. We call that a smooth crossover. However, as we increase the chemical potential to some substantial value, that smooth crossover becomes a first order phase transition, which means that, for example, if you measure the chiral condensate as a function of temperature or the baryon density as a function of temperature, you will experience a gap as you cross this phase transition. Okay. Now, when we present this phase diagram, as you can see, we limit still to small values of mu, relatively small values of mu. Okay. What happens when mu becomes even larger? This is shown here. As you can see here, the authors of these papers were focusing on the very large density, so very large chemical potential, and relatively small temperature of the QCD phase diagram. So here things become more interesting because, for example, depending on how strong is the strong coupling, you could have immediately polar superconductivity as you cross the phase transition line. Or if the coupling is not so strong, you could have an intermediate phase in which the vacuum is still normal, made of normal QCD matter. But then, when chemical potential becomes large enough, it makes a phase transition again to the corresponding conductive phase. Okay. Here there is a similar calculation that was obtained much more recently using FRG, functional randomization group, which shows that basically the same features of the phase diagram that was collected in the previous 2 slides. So basically, at large temperature and small chemical potential, there is a smooth crossover from the confinement phase to the quark-gluon plasma. Then increasing the baryon density, keeping the temperature small, there is a phase transition to corresponding conductivity. So, at least according to this model, very large chemical potential QCD matter is made of a corresponding conductor. It's not normal solution. Questo è lo splitting spinodale. Questo, come? No, questa è la regione in cui c'è la fase non omogenea. Quindi il primo ordine è sostituito da quella finestra in cui c'è la cosa non omogenea. Ok. So, at very large chemical potential, QCD matter is not made of normal quark matter, but it is made of a constant conductor. There is one point in the phase diagram which I did not focus about before, but which I will discuss now. To do that, first, let me go back for a moment to the water phase diagram. In the water phase diagram, as you should know, there is a particular point which is called the critical point. Now, this critical point is important in the phase diagram. In fact, if you follow this phase transition line from liquid to gas, when you cross this boundary, you actually experience a phase transition. However, as you increase the temperature and the pressure at this point, firstly, you will find some criticality, for example, in the specific heat. So the specific heat will be divergent as you approach that point. But moreover, if you go beyond that point and you stay around this area here, it will be not possible to measure any phase transition as you move from the liquid phase to the gas phase. So you will have a smooth crossover also here. So this critical point is the point in the water phase diagram which marks the difference between a crossover at large pressure to a first order phase transition at smaller pressure. For the QCD phase diagram, every model calculation has the same type of prediction, namely that there is a point whose location depends on the model, but still is there, at which the smooth crossover becomes a first order phase transition. This is called the critical endpoint of QCD, and it is the cornerstone of the QCD phase diagram. Because detecting in experiments these critical points would give experimental evidence of a phase transition in QCD. This is why there is a lot of experimental research on the location of this critical endpoint. Here, just for your knowledge, to let you understand how messy is the situation in the community, there is a not so recent collection of data about model predictions on the location of this critical endpoint. As you can see, model predictions are scattered inside the full phase diagram. So at the moment, it is not possible to use the models to say where the critical endpoint is. Different models give different prediction. Okay. Anyway, any model tells us that the critical endpoint is there. Very recently, we realized that the situation might be much better. In fact, the group of these three universities here who make lattice QCD calculations, Ruggieri is also involved here. they use some technique which I have not studied in detail, okay? But basically, using lattice QCD and a small expansion, they were able, I know, they were able to locate the critical endpoint in the phase diagram in this region here. Now, one might have some objection that small mu might not be valid in this region. Anyway, it seems that also people working in lattice QCD community are able to give some more concrete predictions about the location of this critical point. So certainly, this will keep us busy for the next few years. Besides that, there are also collection of experimental data, which now I do not want to claim that this data prove the existence of the QCD critical point, as nobody in the literature has done this claim at all. However, what people can measure in experiments are the so-called cumulants, which means you measure fluctuations of conserved charge. Let's say fluctuations of biolambda, okay, or higher cumulants. Now, what every model predicts is that as you approach the critical endpoint, you would measure a non-monotonic behavior of these cumulants here. So these are model predictions. These are experimental data. You see, for example, for the protons, data seem to suggest that we are measuring some non-monotonic behavior of this quantity, which might be a first indication that actually there is a critical endpoint in the QCD phase diagram. Take this cum granusalis, okay? Because so far no one in the literature said that we found a critical endpoint, but there might be that these are indication of that. Oh, Jesus. Okay, how many minutes? How many minutes?
Actually, very.
Okay, I take
A little bit long, but
I take 2 minutes
We are
because we are finished. You are enjoying it, right? Despite my voice, you are feel. Huh? No?
45 minuti più o meno.
Yeah, you are enjoying them, right? Yeah, just very quick. So basically, we are now starting to study what happens to the QCD vacuum when we have very strong fields, like magnetic fields, as well as polar magnetic fields. We might find something interesting about the response of the critical temperature to these very strong sources. And also, very recently, people started to study more systematically the effect of a rigid rotation on the quantum plasma. Also, we started with very good. So, okay. So, in conclusion, QCD is the modern theory of strong interactions. Bold statement, but it is as it is. The vacuum of QCD is characterized by color confinement on the one hand and conservative breaking on the other. However, when we hit the QCD vacuum or when we fill the QCD vacuum with matter, we expect phase transitions, in particular to new phases of matter, which can be the quark-gluon plasma at large temperature or the color superconductor at large density, in which color is deconfined. So we have deconfined QCD vacuum. Potentially, all these things that I discussed are relevant if we want to understand the dynamics of the early universe on the one hand, or of compact stellar objects like neutron stars on the other hand. And let me finish with one sentence that actually was suggested by ChatGPT. She said, you can finish the talk with this sentence. So I will read it with respect to ChatGPT. So she said, you can tell them that QCD offers a unique window into the fundamental force shaping our universe, from fundamental particles to astrophysical objects. I must say that even though this sentence was suggested by ChatGPT, I totally agree with it. I think that QCD is definitely one of the most important theories on the universe on many scales. Thank you. Yeah, committee wants to ask something.
Basically, the evidence comes from Schwinger-Dyson. How do you have seen? I think.
The what? So,
Regarding the superconducting phase,
okay.
evidence for its existence, aside from we imagine that it exists,
Okay.
is Schwinger-Dyson.
Yeah, mostly Schwinger Dyson, and then models like engineering.
And functional organization.
Also FRGA. That's one of the diagrams that I showed. They claim that it implemented FRG. We can discuss about that, but this is what they claim. So I cannot judge that.
And as for the computation of the critical endpoint.
Or the what?
Computation of the critical endpoint
Okay.
on the lattice.
Or,
Is that the method that uses like the radius of convergence?
no, they are using they call ISO. I don't know how to say that exactly in English. Isoentropic lines, lines of constant entropy. So basically, the idea is that as for the cumulants that I showed, let me show them. As for the cumulants, that when you approach the critical endpoint, become non-monotonic. When you study these particular isoentropic lines, they get some non-monotonic behavior. So studying that change in behavior of these lines, you can guess that there is a QCD critical point. Yeah, one can make discussion about the radius of convergence.
There are studies that study like how the curve should go.
Yes.
And then radius of expansion study, because it should diverge, that the radius of the expansion should become infinite at the critical endpoint. So they have those steps.
Now, this I don't know. You mean that, so you are saying that the radius of convergence is infinite at a particular point?
The radius of the expansion
Okay.
that brings the lattice to finite chemical potential.
Okay. And that's infinite.
Yes.
How do you prove that?
Because you have a discontinuity and you can do whatever expansion there. So it's
I know, but how do you know that? I mean, from first principle QCD.
You can't do a Taylor expansion around.
Yes.
Because you have a discontinuity and you have.
But you're talking about lattice QCD or in general?
General, if you have a transition.
Oh, okay, I understand.
From one side, you can do it.
Okay. If you okay, I can give you some physical argument actually. If you are near the critical endpoint, you will measure critical fluctuations. So the fluctuation will be divergent. So that's the signal that you should look at for this particular point to be present. At the moment, there is no evidence at all about that. Even if also on the lattice now they start to measure these non-monotonic behavior of the isotropic lines. In experiments also, it seems there is some non-monotonic behavior of these cumulants. But from that, stating that that is evidence of the critical endpoint, I don't know. What?
Okay. That will thank again Professor Ruggieri for to the next meeting. Thanks.